So we're moving to the final presentation of the session. I didn't memorize the title instead of authors. It's going to be given by Kevin, and he's also going to tell us what the title of the work is, and we're very excited to hear about it.
Hey everyone, so I'm Kevin, and please excuse the very ballistic title slide, but I'm going to talk to you guys about a piece of research software, visualization software that we've been working on. And I'm probably going to spend 10 to 15 minutes talking about it, but also 5 minutes talking about the future of this work. But before I get started, if you'd like to, you can scan the QR code to get the slides here. And it's recommended to do so because we're going to have some demos and also some links to other related works if you're interested in that. So maybe just if you're done. Okay. All right, does that work? All right, excellent. So we'll be moving on. Okay, so got a sneak peek of the next slide here. But let me set the scene, right? So visualization has always been man's best friend in understanding. Whenever we wanted to explain something or understand something, we drew pictures. So here are some of the pictures I drew in my notebook. The one on the top left, it was something about differential heuristics. The second one there, something about task assignment and network flow. And the other three, honestly, I had no idea. I have no idea what those are about, but I trust that past me found it really useful to look at those pictures and kind of like draw something out and think about it. And just the other day, I caught Nathan and Andy discussing something. The problem itself, it kind of goes over the top of my head, but really, you know, visualization facilitates exchange of ideas and quality discussion. And then we have examples of tales of famous people solving famous problems on the back of a napkin. So here we have Jack Kilby from Texas Instruments, who sketched up the first idea of an integrated circuit in his notebook. Visualizations don't have to be beautiful. They just have to be useful to help us think about a problem, to catch errors and misunderstandings, to see new patterns and come with new ideas and have that moment of spontaneous brilliance. So let's get more specific now. In the space of search, people have been working on a bunch of different tools for visualization for all sorts of things. So visualization in the form of charts and plots, visualizations, as we might be familiar with, trees, decision trees and planning trees and graphs and all sorts of things. And we've got visualizations for the purpose of education. Got visualizations that are domain specific. So there are a lot of visualization tools out there for search. And they all have their purposes for debugging, for insights, and they're all super useful. But let's turn our attention to the case of what if we want to use visualization for myself? So when there is something out there, like this one for multi-agent path planning, great, just pick it up and use it. But oftentimes, well, there isn't something off the shelf that's available to us. And we kind of resort to, and you know, these problems coming also shape and sizes, right? So different domains, different algorithms, different procedures. We work in different languages. And sometimes you just want to see different things, right? So it's kind of no wonder that like oftentimes we don't have something off the shelf to use. So resort to the sort of common techniques for debugging, like writing logs, and I would usually very oftentimes just like put hello 1, hello 2, hello 3, hello 4, and to try to figure out where my algorithm goes. Debuggers, right? So if we know that there's a specific piece of code that could be wrong, we can boot up a debugger. We can do something from scratch, so these are real, by the way, so these are real logs produced by people who are working in search, and this one is a kind of a matplotlib that was hacked together to kind of represent a grid map, or network map. And as my dad would try to tell me, just to think harder, although I can't really, I don't know how to do that. So I'm a research engineer, and by nature, I think all day about how can we use software to help people in research. So we can't create a visualization tool for every person for every problem. So that's a bit silly. So we got to come up with some sort of framework that helps us do that. Something that makes a small set of assumptions, so it applies to a wide range of people and problems. But they also have to be powerful assumptions that probably applies, or as I say, 9% of use cases. This framework should have some way, since we're trying to understand algorithms, some way to record what happens in an algorithm. And of course, some good way for us to, for the person working on the algorithm to create visualizations. So we are not trying to create the visualization for them, but we must provide some way for them to easily create those visualizations. And that's what the Posthoc project is all about. So Posthoc allows you to record program execution in a particular way, and then to be able to take that artifacts and to get access to a wide range of analysis tools. And if you'd like to try out Posthoc now, you can also scan that QR code. But let's set up some expectations. So we're not looking at very beautiful, very complex visualizations, but we're looking at simple but effective visualizations. And we're not trying to replace any tools. This is something that you would add to your toolkit. It comes in two parts, the search trace format and the Posthoc visualizer. And in the next few slides, you might feel like the search trace format is rather kind of an insignificant thing compared to the amount of work put in the Posthoc visualizer. But actually, the search trace format is what kind of makes this whole thing work and kind of ties this system together. Okay, so I'll give a brief intro of the two things, but we'll leave time for the demo, and I'll explain things in detail more in the demo. So search trace looks like this. It is a textual recording of your algorithmic procedure and an optional description of the visualization model. So the event section there, that is a recording. That is what's produced by your solver. And on top there, that is something you write to kind of explain how to convert those events into visualizations. Again, we'll look at this in a second. And why YAML? So as you may be able to tell, that's YAML. It's kind of, I think we've seen a lot of YAML-based stuff recently. And it's just standing on the shoulder of giants. So it is a really well-defined format, and it's a really powerful format. It's also a superset of JSON. So anything you write in JSON, if you can log stuff in JSON, still works as YAML. And there's just a lot of a really good ecosystem. There's a lot of serialized and deserialized out there. So it's super easy to read and write for people and programs. So I mean, I could go ahead and just write this document, but for programs, you could literally just do like print statements to create that document. So it's super easy to integrate into any program. So I have some example there of just a few lines. It's a bit hard to see, but there's a few lines where it's just doing some print statements. And some solvers who are compatible can maybe generate them if you give it an argument. And then you can also write small examples by hand if you want to just test something out. Now, when we have a search trace, what you do is you drag and drop that into the Posthoc visualizer, and you can get access to a whole bunch of analysis tools based on that one file. So things like being able to replay the execution of the algorithm, to be able to see it in the visualization, both as a tree and also your custom visualization. So that's what's defined at the top of the file, and we'll see that in a second. Other features like breakpoints and all sorts of things. Okay, so now we get to a demo. And this is where we kind of wing it, because I haven't done this before. And you can follow along, by the way. So if you have a laptop and you have the thing open, you can also do this. And it also works on your phone if you like to try that on your phone as well. Maybe the screen is a bit fidgety. So let me explain what this is. So this is Piglet. So Piglet is one of the solvers that support Posthoc. And this is something we use for a unit that we teach at Monash. And you get this is a pathfinding search solver. But you get the search trace output if you in the command line add this -- log trace. Can everyone see that? And I have a quick video here to show you how that works. So just kind of just put in that command there, and you get that search trace that we've seen. And so what you do is you just drag and drop that into Posthoc. So this is the first your first time seeing Posthoc. I'll probably explain the UI a little bit. So these are different panels. You might be able to tell. You can drag these things around like this. Okay, and here are your imported files. So there are two files in this visualization. There's a map file here, and there is a search trace that we've just that we've seen just then. And I'll start with that search trace. So I'm going to switch over to the sources view. So these are the files we've imported, and this is what the file kind of looks like. Okay, so you have these events here. So we reckon that for most of the cases, these problems, these things that you could visualize can be modeled as what we refer to as a chronology. So chronology can be as simple as a list of events, but chronology also implies well, an ID that identifies one node per se in a search tree, and its parent optionally. So this is modeled here as the ID and PID. Can everyone see that on the screen, or is it a bit small? Is it okay? And so the list of events, and up there, I'll quickly explain how this works. So here we're saying this is kind of a mapping of each event to one visualization. So you can kind of think of it as a loop. So one event, and this is how to render it, and this main kind of implies that this is the entry point. And we're basically saying that for each of these events, we want to draw a rectangle. So this means to draw a rectangle. And for this rectangle, we want it to be width and height of 1. And we want to bind the x and y position of this rectangle to what is here referred to as $.x, which is actually pulling data from here. So this is saying this number here, these numbers here, will be bound to the x and y position of the rectangle. So it's that simple. We're just drawing rectangles here. And this one here, so by the way, so these brackets here imply that there's a custom expression. And this here specifies the color of that rectangle. So it's that simple, right? And what we get here, okay, so let's go back to the report. So what we get here is a visualization that looks a bit like this. So that's pretty nice, and you know that's much better than staring at a log. So it's that simple to get something quick and easy on a screen. And we can do a bit of like playing around. We kind of press on things and look at the information and kind of skip around and kind of do that. And if your search trace contains these ID and PID, so these are optional, but if you have these two, so then your chronology is a graph. And you enable this graph view. And you can kind of see the same thing happening here, like that. So you can, again, just like go around and play around with this and explore the search process. We have a few really cool new features here, like being able to see the precedence. So what actions, what states result in the current state here. So really cool. Okay. So I want to show probably one more example, so like a medium level example. And then the rest, I highly encourage you to go onto the main site to play around. And the simple kind of idea, the simple system kind of goes quite far. And there are some really impressive things you can do with it. So the other one I want to show is probably this 9-tile puzzle. Are you guys familiar with the 9-tile puzzle? Okay, cool. So it's a very a classic problem in heuristic search, right? So this 9-tile visualization looks a bit like this. So it's quite nice. So this time we're visualizing one state in the search. So it probably makes more sense to bring up the graph as well. So the search looks like this. So again, really cool. The thing I want to show you is how you can use that visualization language to get more complex behavior. So here we have a little bit more code, but actually not a lot more code, right? So that's not too much code, and I understand that it's probably pretty hard to read as a first timer. So let me try to talk you through this. So this time in your events, so this is the thing that is logged by the solver. We also record the contents of the board for each of the events, and pretty much what this is doing here is to translate one event, this board information, this board data, into the tiles here. So there are probably two new concepts here. So one is that the tiles. So what we're rendering in main. So this is the entry point. It's not rendering a primitive like a rectangle, but it's rendering this thing called a tile, and it's something we define here as a rectangle. And this is something that we can kind of reuse. We can also pass properties to this. So if you're familiar with like a front end language, like just to give one example, React, this is kind of how it works, right? So you kind of nest these components together, and you can pass properties into each other. So what we're doing here is doing a for loop. So rather than rendering one rectangle or one tile, we're rendering 9 tiles here. And for each tile, we're going to give it a particular column and row as arguments. And these two properties are consumed here. So these properties, they eventually come here to position them at specific X and Y locations, and also to infer certain information about it. So just to give an example of where that goes, so this is the label, and this controls the text, and probably do add 1 or something like that, and you can probably see all the numbers increased by 1. Okay, so I think this is this system is super cool, and just to give you an idea of all the cool things that this thing can do. Well, so we have the basic A-star example. We have this kind of post-game analysis that captures a StarCraft match and kind of visualize also the aspects of it. This is something. Maybe if we have time, I'll show this. This is something really cool. Kind of leaving that as a mystery, but okay. So let's go back to the presentation. So the whole idea of Posthoc is to make visualization more accessible. And I don't think we're quite there yet, right? So I don't think we've hit that goal. And one of the things you might notice is that I kind of barely talked about stuff like PDL solvers, and you might be wondering what it is. And the basic thing here is that to use Posthoc, we still do need first-party support from solvers to be able to produce that search trace. So as a user of a solver, you can't really go into the source code and kind of add new stuff in there. I mean, you can kind of hack something together, but so dear solver developers, so if you'd like to make it easy for for users to inspect the algorithm procedure of your solvers via Posthoc, please consider supporting Posthoc as the search trace as the format of your the search trace as the logging format of your solver. And you're probably doing logging already, and the YAML format kind of doubles as a regular textual output format already, so human readable format. And so it might be a super simple switch to make it compatible with this. And for tool developers, so if you find Posthoc useful, but maybe it's missing something, so just remember that, as I explained before, the core of this project is really the search trace. The search trace is not inherently tied to Posthoc, and so consider building tools that support the search trace as the format that it takes in, and that way we kind of use the search trace as the point of interoperability. So what I mean by that is, like, anyone with a search trace can now get access to a massive suite of analysis tools, and I think that is a super cool idea. Another thing I would like to quickly touch on is the idea of making progress in search and planning more discoverable, and I think that's doable with the Posthoc search trace ecosystem here. And it's not a thing yet, so the picture I put here is just about just like the examples we give on the Posthoc application. But the idea is just that in the future, perhaps anyone can create and share this sort of visualization publicly or privately. And so if you decide to polish up on your visualizations for the purpose of sharing it with the world, that it'll be super easy to do that. And the last thing, which I won't really go into too much detail, is the future of the Posthoc visualizer. So one thing to note is that Posthoc is designed to be super extensible. You can extend it in a lot of different ways, like component libraries. So that tile that I showed you, so something like that, but something that could be reused more often. Renderers are currently it can only do 2D, but we get requests to maybe have 3D support, so you can kind of plug in renderers. But that's not done yet, and I think 3D, one more dimension to play with. We got to get to that. So direct solver visualize interactivity. This is referring to something we've not really looked into too much, but the idea that the visualizer can directly talk to a solver and pull things out. So that's kind of to explore sort of what if scenarios and kind of be able to close the loop of like of that, like kind of specifying problems and getting solutions and that sort of cycle. And if you'd like to just support Posthoc in general, please start us on GitHub. Try out the app for yourself and see if it works for you. And now that you know Posthoc, maybe it will help you with whatever projects that you're working on. And that's where the story is at so far. And I don't really know how to conclude this, but so maybe I'll say something like, so advancing visualization tooling in search is a community effort. It's something that grows with the communities together. So let's write the next chapter of the story of search visualizations together. Thank you. So before we do the questions, I'm going to try to put something in the background and just let it just sit there and you can answer questions.
Can I ask now?
Yeah. Hi.
Hi, thank you. And I'm kind of thinking of writing this in my framework.
Yep.
My question is, when I debugging a search algorithm, sometimes I found strange behavior in relatively where we have million or even billion of search nodes.
Yep.
In such case, visualization work, I mean, can we somehow observe a set of states so we can easily see the overview of search?
Very good question. So we've designed Posthoc to be quite scalable, but we're still having some trouble hitting the million events point, and we are working on that. So introducing some way of like partially loading or lazy loading bits of the search trace. But we have some examples of like really large search traces and really large problems. We have a network map example of New York. So it's loaded the entire New York map, and it's like doing a search from one place to another. And that's got like 1 million elements to it. It's not events, but it's got 1 million elements. So you could try applying your problem to Posthoc with the large problems, but if it's not possible, maybe soon down the line we'll have something that supports that use case. Yeah. So I'm just gonna play this. It just goes in the background. It's just so it's an animation one of my friends made in Posthoc, and I think it's super cool. So.
How long did it take you? How long did it take you to get to this point?
So Posthoc has been a project for a while, but I think the most progress came from when I did my honors. So I spent an entire year working on this, and we've also got a lot of different students over the years to kind of contribute a little bit of this and that. But really, it's although it kind of it's already finished playing. So although it looks pretty powerful at the moment, I think this is it's not really hit its full potential. So we'll see how this thing develops in the future. So let me actually take this to playback rate of 1. Okay.
All right. So let's thank Kevin again.